turn the sound up so I can hear. All right, so today I'm going to be presenting on sensing on strange new worlds. So this sort of ties into some of the research I've been doing with the ACFR, particularly over the last sort of 6 months. And I sort of want to bring in a number of sort of fundamental concepts in the field of robotic imaging and relate that to space engineering, which is a really exciting, up and coming and growing field in Australia. So to start off, I think it's always good to give a bit of an introduction. So this is me, engineering mechanical. So you'll notice that this is going to be a very Tron heavy talk, which will be interesting, and you can sort of get a bit of an idea for how flexible engineering degrees really are. I'm going to be talking a little bit about space engineering and some underlying physics throughout this. I'll be doing an ESIPS in semester 2 with Nearmap, which is again a very Tron-y type thing. I was an engineering leadership scholar, and I've been working as an undergrad research student with ACFR, and in particular working currently on a paper, which I'll share a few more details about as we go further. So this is the Robotic Imaging Research Group where I work. This was us in January 2020. It's headed up by Don Dancero just there. So if you see him around and you're interested in some of the things I present about, feel free to drop him a line. I'm sure he'd be more than happy to share a few more bits of information. Engineering as a whole thing is really exciting. You get to go to a lot of really interesting places with it. So on the left-hand side here is me in Cambodia running some engineering outreach workshops at the end of 2019 as part of one of my roles with the faculty. The year before that, I was in Hong Kong on a 3-week research project with PwC. And then also in 2019, a bit earlier, this was an activity I ran as the president of the Mechanical Undergraduate Society, where we had Ord Vignell from the Australian Space Agency come in, and also Dr. Paul Scully-Power, who was the first Australian in space, which was exciting. So you get to meet a lot of really cool people and go lots of awesome places as part of engineering. So one of the sort of themes about space engineering is this concept of the unknowns. And one of the things we want to do is we want to minimize those unknowns. So this here, I think, sort of exemplifies this, pretty much in its entirety. This is a website called Stuff in Space, and basically it tracks everything in space. And we do this for a couple of reasons. We know that there's a lot of stuff up there, and we know that we're going to be sending more stuff up there. And so we don't want things to crash into one another. And in order to prevent that, we actually need to accurately track to minimize these unknowns. Now with rovers, there's a lot of things where you actually can't minimize these unknowns. And so what you really need to do here is look at equipping your spacecraft with ways of dealing with the unknowns. And so to do that, you need to give whatever you're designing a suite of sensors, instruments, and cameras to feed back information and give something that can inform its decision-making process. So if you were in that environment, what would you need to get a better understanding of it? That's sort of the mentality you need to approach. And so you've sort of got to put yourself in a very weird position in that you might be, you're never going to set foot on Mars, most likely. You're never going to set foot on Venus, that's for sure, because it's pretty dangerous. But you need to think about, if you were there, what sort of things would you need to be able to fully understand the environment and deal with those unknowns? And so it sort of is a bit difficult because you've got to do that years and years in advance. Anything you send into space is likely a one-way ticket. So for example, we're never going to get Curiosity back. We're never going to get Perseverance back. And for sure as hell, we're not going to get anything we sent to off-world asteroids and Venus and all those sorts of things that have been severely damaged. And so we need to make sure that whatever we're designing it with is going to stand, number one, the test of time, and number two, be able to function in a reliable manner. And so to do this, a lot of the technology that actually flies ends up having to be set in stone years and years in advance, sometimes up to 10 or 15 years. And again, it comes down to this idea of it's going to be a one-way trip. and you better make sure that it works. So where are we going to send our rover? That's the sort of next idea. Does anyone know what this is a picture of? Feel free to type it in the chat, or there's a couple of people in the room here. Feel free to shout it out. Yes, Steve.
Is that the surface of Mars?
That is not the surface of Mars. Yes, Michael had it. It is a Russian probe on Venus. In fact, it is the Venera 13. Now, when I look at this photo, I sort of come from a bit of a robotic imaging perspective. So I look at this and I thought this would be sort of a good exercise where I break down what some of these things are showing us. So some first impressions here is we look at the color of the sky. It's this sort of weird off yellow shade of color. And this is the result of some atmospheric scattering or some sort of dust in the atmosphere. And so we need some way of dealing with that. If we look at the surface here, it's pretty textured. There's lots of nooks, crevices, crannies, you name it, it's got it. And this is actually quite hard to visually sort of classify, analyze, and navigate through. This is actually, we like having texture. In this case, it's probably too much texture for our rover to be able to deal with. Another thing is this idea of visually similar scene. So for example, if I were to take this sort of block of the screen here and compare it to this block of the screen here, you'd probably have a hard time working out where those blocks were placed in this image. And for robots, that's quite a difficult thing to deal with. The algorithms we design rely on the concept that we can very easily work out what things are different. Now, in addition to this, this isn't dealing with the fact that Venus is incredibly hot. It's also not dealing with the fact that the atmosphere is basically sulfuric acid, and so whatever you send up is going to be melted away quite substantially. And so there are additional things that we need to consider as well. Now, if we look at Mars, this is very different to Venus, as I'm sure you'll agree. We have here some really nice color variation. So I can tell where the regolith of Mars is and where the rocks begin. That's quite easy to work out. We also have some really nice sparse and well-defined features. So what I mean there is we've got these sort of big things that we can visually segment and identify. And the algorithms that we design rely on being able to do this. So for example, rocks are quite easy to pick out. The gravel in the ground is quite defined in shape and distribution, and we can work out where all those are. Now, we also have some really nice things in terms of shadows, so we can actually work out where the lighting is in this scene. It's also nice and diffuse, which is great. And this seems really, really promising. And indeed it is. If you look at some of the images that we've got from Mars, they're fantastic. We're able to basically get a really good idea of what this environment is, what it's got, what it's hiding, and essentially design rover systems to be able to deal with this. In terms of unknowns, we've effectively minimized it. But there is some additional things we need to consider for Mars. So this is what makes Mars challenging, the concept of weather. Now, Mars has an atmosphere, much like we do here on Earth. And so the net result of that is it ends up having weather phenomena. So what I've got here is some things that have been pictured by previous Mars rovers. One of these by Opportunity, another one I think could have been by Curiosity, but essentially what they're imaging here is what's known as a dust devil. So this is sort of the wind on Mars whirling around a lot of dust in almost like a tornado, like what we would get here on Earth. And what this tells us is that there's a lot of regolith movement around Mars, and that's probably going to coat a lot of our things. And indeed, this next picture sort of shows that. This is Curiosity taking a selfie. And in the background here, you'll notice that there is something very large and ominous booming. If we look at the sort of condition of Curiosity after a couple of years on the surface, you can see it's coated in this really fine dust all over. Now, this isn't a problem for Curiosity. It's been designed to do that. And in fact, it's got a radioisotope thermal electric generator sitting here on the back, and that's what provides the power. But If we were to design this to be based off solar panels, it would most likely be quite a different story. We'd need to have some way of dealing with this dust. And so that sort of comes into our consideration as well. When we think about camera systems, we don't want dust on our lenses. For example, if you try to take a picture on your phone where it's pretty dusty, you're going to end up with terrible quality pictures, as I'm sure you'll agree. And so we need to have methods of being able to deal with this again. This actually provides an unknown. So it would sort of be like driving around in fog without lights and your battery is running out, as was the case with Opportunity on Mars not too long ago. That sort of led to the demise. He got caught in a really big dust storm. His systems had already been degraded. He'd exceeded his mission life, was doing fantastic things, and unfortunately, the weather sort of came over him, as we say. And he will forever be on Mars in the last state that we left him in. But he did good. He was a good rover. I now want to move on to the moon. Now, you probably think that this isn't a place where there's a lot of unknowns. And you might think that because we've been there, right? We've sent humans to the moon. They've been able to set foot and really get a good understanding of the surface, right? Well, in actual fact, that's probably not an accurate description of how space exploration happens. And so if we look at the polar environments of the moon in particular, there's a lot of really weird things that we don't see here on Earth. So in terms of light, we have what's known as atmospheric attenuation. And so that's where light comes in from the sun, hits an atmosphere and is scattered and ends up sort of reducing the intensity for one and producing this really nice diffuse lighting on the surface, as we saw on Mars not too long ago. What we also have near the poles, and this here occurs on Earth as well, is this shallow illumination angle. So over here, we've got some features that could be on the order of kilometers tall, and the shadows that they're casting are on the order of kilometers long. Now, if you think about it, your rover's pretty small. It could be, say, 1 meter long by 1 meter wide, for example. And if it's casting a shadow, if one of these features is casting a shadow kilometers long, well, you're going to be in shadow quite a long time. And so that causes a number of challenges. How do we deal with that? How can we actually sense in shadows? These are also really fast moving as well. So this is a simulated pole illumination over 28 days. And so at the very tips of some of these shadows, they're moving on the order of centimeters per second, which could be faster than your rover is actually moving. The other weird thing about the polar environment, and indeed the moon as a whole, is this concept of retroreflection. And so this next slide shows this quite well. So these are from Apollo 16, which was in what's known as the Highlands environment of the moon, which is where you've got this really grey, light grey regolith compared to the dark grey that you get where, say, Apollo 11 landed, which is known as the mare. And so if we look here along the sun vector, it appears quite a bit brighter than it does across the sun vector. In addition to that, we also notice that across the sun vector, we also were able to work out where all these rocks are, whereas on the left-hand side here, it's pretty difficult. And so this is a lack of texture, essentially. And so if we were to sense or try and sense in this environment, there's a number of considerations that we need to make to actually try and correct for this. Now, the reason this retroreflection happens is because the moon does not have an atmosphere. So when you have these little meteorites come in, they smash the surface of the moon. And so bigger rocks end up being macerated into this really, really fine powder. When you have a really fine powder, you have distances between particles about on the order of size of the particles themselves. So when light comes in, it undergoes what's known as the coherent backscatter effect. And what that means is light goes in and has a tendency to reflect out at the backscatter angle or the retroreflection angle, which is directly along the illumination angle. And so if we're looking with the sun behind us, we can sort of see that we have an issue. We may not be able to sense on this surface. The other thing is the moon is low gravity, and because the particles are so fine, you can actually have particles levitate above the surface. The surface of the moon can build up an electric charge, and so some of these particles can stay levitating in this sort of electric sheath above the surface for sometimes years on end. And there's some really cool photos that the astronauts have taken when they were taking off from the moon. It's called the horizon effect. I recommend you go have a look at it. You can actually see this glow where the sunlight passes through these suspended particles of moon dust. Now, the next thing to look at is in-orbit robotics. Now, this here is a video for the birthing of one of SpaceX's Dragon resupply capsules. And you can see here that orbiting around the Earth, we have really, really nice lighting. But in some cases, we actually probably have too much lighting. These are really, really bright scenes. Again, there's no atmospheric attenuation. And so we need to have methods, and you can see the lens flare here, it's quite substantial. Have methods to be able to deal with these really, really bright, high dynamic range scenes. And when I talk about high dynamic range scenes, I'm talking about the fact that in part of the scene, you have complete pitch black, and you can see that with the depth of space. But you then also have these really bright, intensely illuminated parts of your spacecraft. And so again, this comes down to minimizing the unknowns. If you can't see because things are too bright and your sensor is overexposed, you're likely going to have some serious issues. And so you've got to come up with ways of dealing with that. I'll just let this dock very quickly because it's a very cool video. I probably spend too much time watching these. But yeah, sensing in this sort of environment is not easy. If anything, sensing on Mars is probably easier than sensing from the International Space Station. Okay, so the next thing is about small rocky bodies. So I've talked a lot about planets. I've spoken about looking around in low Earth orbit. Now I want to talk about what about these really small rocky bodies. And again, this is really difficult. You might not have illumination at all, so you need to have some way of being able to actually sense on this surface. And if you were a robot, in fact, you probably wouldn't want to be maneuvering around very much on this with wheels. There's some really, really sharp rocks. And this is Ryugu. This is where the Japanese Hayabusa 2 went and visited, and some of the pictures, it's returned from there. Some very interesting stuff, but not a nice, easy place to sense on. So a sort of a segue from there, this is something that might seem fundamental to quite a few people, but I think it's important to actually understand when we talk about taking a picture or using a camera on something, what are we actually looking at? Or how does that light end up being the pretty pictures that we know today? And so if we take one of these cameras here on Curiosity, for example, fundamentally it comes down to a few things. We have some optics which work to focus the light, and it focuses that onto a sensor. Now this sensor, each little pixel on it is almost like a bin. And so when the photons hit, we want to amplify that signal. It's quite a small signal, so we have some amplification here. We then want to convert that into something digital. We like to work in digital, nice and easy. We're very familiar with that. And so we pass it through an ADC. And the net result is we end up with an image. In this case, it's a color image. So we have what's known as a Bayer filter, where we have red pixels, green pixels, and blue pixels. But you could very well have monochrome pixels as well. Now, an important part of this is even just by capturing this light, we're introducing noise. We have an amplifier here, that's subject to noise. We have an ADC, that's subject to noise. And we also have the fact that these photons are not necessarily a continuous stream. They come in pulses. And so there's noise related there as well. And that's something that we need to be aware of and could impede our sensing. So you might be wondering what's so good about an image? Well, humans are visual creatures. We've evolved to have eyes, and that's for a reason. Images give us a really nice, dense information representation. They're very cheap in terms of data and energy. It doesn't take a lot of energy to actually capture an image. And we can provide a lot of things just from light hitting a sensor. And so this is where I want to introduce the concept of the planoptic function. Now, what is the planoptic function? Well, the planoptic function is essentially what is the most that we can ask a camera? What is the maximum amount of information that we can actually obtain from light hitting a sensor? And so we can get a couple of things. We can get the angles of light passing through the aperture. So the angles will come in and hit a certain pixel, and we can sort of work out based on how the optics is designed, what angle they came through. We can also work out the wavelength of light. So light comes in a multitude of different wavelengths, and it will hit the sensor and produce a different response. So we can sort of work back from that and work out what sort of wavelengths hit what pixel. Over time, we can integrate to actually form an image, so have a longer or shorter exposure. We can also take movies as well. We can also look at the polarization, if we chuck a polarization filter on our camera. And we also look at aperture pose as well. So where was our camera actually pointing to collect this light? Now, regular cameras only look really at a subset of this. Now, we get the angles, and again, we can work that out by the fact that we have some optics and we know what pixel the light has hit. We get a subset of the wavelengths of light in the visible spectrum. We can work out the time because we can capture videos, so multiple images over multiple periods of time, and each of those actually integrates over a very short period of time to form an exposure. And we really only have this one pose. We define it as the X direction where the light comes in parallel to the camera aperture. Other cameras, however, can give us a range of different combinations of this planoptic function, and also sometimes a greater range as well. And so when we think about robotics, we can actually use this to our advantage, and we can sense a number of different things. So the next sort of concept is, well, okay, we can capture images, but robots really need to have a good understanding of what is in their surroundings, their sort of spatial awareness. Now, this here again is our model of Curiosity. And I want to point out a couple of things. So over here on his mast, that's where his eyes are. And you can see here, he's actually got 4 navigation cameras, 2 on the left, 2 on the right, and they're separated by a distance. Now, this is how he's able to sense depth. It's a thing called stereo imagery, and it's a reason why we actually have 2 eyes. It enables us to be able to perceive depth. And you can try this at home. If you cover up one eye for a really long period of time and then try to pick up your mug of hot tea, chances are you're going to spill it over yourself. Don't do that. Make sure it's a mug of cold tea beforehand. But that is how humans sense depth. And it's also how we get robots to sense depth as well. So we have 2 cameras here, and they're separated by a distance b. That's known as the baseline. These cameras have a focal length, and we want to work out where an object O is in our scene, and that's some distance. So we can work this out. You'll notice there's an unknown parameter here, d. This is what's known as the disparity, and I'll get to this in the next slide. But essentially, we take 2 of these images, we compare how similar they are, and we match them up, and we work out how many pixels we need to shift each object in the scene to be able to get it to match up with its pair. We can then do what's known as a camera projection, and what this does is it transforms us from image coordinates U and V, so that's your sort of X and Y in image coordinates, to your X, Y, Z in space. And that gives us essentially a point relative to where those cameras are that enables the robot to sense depth and work out where things are in the space around it. So these up the top here are what's known as stereographs. And I was talking about before this concept of disparity. Now, we define disparity as, let's take this rock up the back here, right? We have this blue rock and this red rock. One of these, the blue one, is from the left image, the red one is from the right image. And this concept of disparity is, if we took this pixel here, how many pixels over do we need to shift it to get this red rock to line up with it? And that gives us a value, a number of pixels that we then put into this equation here. And that's our disparity. And that's how we work out depth, basically by similar triangles. Now, what's interesting is this concept of dynamic range that I introduced before actually is a real struggle for stereo. So if we look here in a low light scenario, we have a crater and the inside of this crater is shadowed. When we look at this disparity map, when we've gone through and done a matching algorithm, which is where we try to work out which pixel corresponds to what in both our images, it really struggles in this region. In fact, it doesn't do very well at all. And the same thing happens here, though to a lesser extent, when we oversaturate things. So this rock in particular, right at the front, is heavily oversaturated, as you can see here, and it means that we're not really able to get a good fix on what it is. And this introduces noise into our depth information. Now, what I've got here is some simulated depth images, one from the left and one from the right of some work I did over summer on some lunar rovers. And basically, we've gone through and done a stereo matching algorithm. So we've taken this left image, this right image, and we've worked out how far we need to shift these pixels over to match them. From there, we're able to get depth. And from there, we can actually project this into a 3D representation of the scene. So you can see here me moving around these boulders, and you can get a good indication of how far back these back boulders are. You also get a bit of a lip of a crater there and the slope of this terrain as well. And this is really what's happening on most rovers. In fact, almost every single rover has used stereo. We're only just now really looking at other opportunities and other sensing methods to obtain this depth information. So let's go back to this image for a moment. Would stereo fail on this? Well, likely yes. If we look at it, there's a lot of visual similarity. Our algorithms could not work out if a patch here was here or was over here or was down here somewhere. And so there's not enough texture in the scene. And so how do we fix this? Well, what if we create some texture? And this is where I want to introduce the concept of burst imaging. Now, burst imaging is a pretty interesting, a new up-and-coming technique. And it's basically where instead of taking a single picture of a scene, what if we were to take multiple, merge them, and get rid of the noise? And so that's what I've done here. I've got a 47 frame burst of this pile of salt. I've then reconstructed it into one image. Now, you can't really see much difference between these, but if I contrast stretch it, and that's where basically I take the histogram of all the intensities of light and stretch it, you can see here that the single frame has lots and lots of noise, whereas the burst reconstructed minimizes that noise significantly. So Steve has asked a good question. You're stacking the images to get rid of the average noise. Yes, that's correct. You also take a burst with the lens cap covered, and that actually gives you the intrinsic camera noise as well that is just sitting in the background that you otherwise can't see. Good question. So anyway, how do we actually quantify this texture? Well, so what I've done here is some entropy, standard deviation, and range of some local sort of windows within these pictures. So this is the single frame, this is the crappy one, and you can see there's lots of local entropy related to that noise. Whereas, if we look at the burst reconstructed, we can actually get to see where all these little curves, nooks, and crannies on this pile of salt is. In fact, we're actually able to reconstruct where the tripod standing behind this little tray here is sitting. And we see a greater improvement in a range of these as well. And so what you could possibly do is take two stereo cameras, burst them, undergo this burst imaging process, and be able to reintroduce some of that texture that you otherwise couldn't see after contrast stretching. So the next thing is probably something a lot of you will be familiar with, and it's the idea of LiDAR. It's using light to be able to work out the distance to things. And the way it works is pretty simple. We have a laser, we shoot it, it hits something, returns back, and we can use the time of flight, so how long it took for the light to be emitted before it was detected, to work out how far away it is, the range. And we use this quite substantially on Earth. For example, here we've got some SLAM some self-localization and mapping, where this is going through and generating a map of this terrain, and that can be used for navigation purposes. We can do that on the moon as well. And in fact, here's one of NASA's up-and-coming projects that will actually have a LiDAR mounted on it to be able to obtain a lot of this depth information. The good thing about LiDAR is it's really, really accurate and sort of low computationally intensive, in that it's pretty much one equation to work out how far away things are. But it's prone to some errors, and this occurs a little bit in that retroreflection I was talking about before. So we have here the depth of the scene, and you can see some funny sort of creases here. This actually corresponds to retroreflection. So what I had here was a black sheet with a whole bunch of little glass beads on it, and I took a Intel RealSense LiDAR, imaged the scene, got that retroreflection, but I also noticed that the mound of glass beads was actually into the page when I should have expected it to be a nice mound sitting on top. And so what's actually happening here is the light interacts with the material. And so rather than just having this nice time of flight here, where you assume everything has a refractive index of 1, you actually need to take into account a couple of other things. You need to take into account the fact that it's going through multiple materials and it's interacting with that material. And so as it goes through, it's going to have what's known as a characteristic interaction time. And so rather than having that T just for the entire thing, we actually need to work out how long it's taken between all these bounces and interactions to accurately work out what that range is. Now, this is a change of about 3 to 5 millimeters, which doesn't seem all that big, but let's put it in context where if you have a rover and you have an error of 3 to 5 millimeters on everything, and you're propagating a map, if you've got a mission life of 5 years or so, and you're doing that, every 6 seconds, that can add up quite significantly. And if you're using this for localization in particular, you could be meters off by the end of your mission life, which may be an issue or it might not be, depending on what you're trying to achieve. Now, LiDAR has seen use in space, but it hasn't seen use on a rover yet. And so this here is OSIRIS-REx hitting the asteroid Bennu. And this actually had a LiDAR on it, a flash LiDAR, to be able to work out how far above the surface it was in order to capture its sample. Let me play that again. This is quite a cool video. And this also shows why cameras are so important, because when robots and space engineering things do cool things in space, we want to capture them for our memories. Now, hindsight's really good. Rosetta was this mission that the European Space Agency had, where it launched this little Philae lander down to the surface. Now, what they've said is if Rosetta had a LiDAR, this little speck, this micro body that orbits around Comet 67P, they might have been able to map and actually work out what sort of gravity it had and why it was sort of pinned in orbit around this comet rather than sort of zooming off elsewhere. But it was good that they did have a camera, because that little Philae lander, well, it didn't actually land, it crash landed and ended up in this nook and cranny over here. And so it took them a bit of time to actually work out where it had gone after it had supposedly touched down. Luckily, Rosetta had a camera, because we now work out that, yeah, it bounced, didn't go into the surface like we would have wanted, and unfortunately couldn't achieve all its mission objectives. The next thing is about localization and visual odometry. So I mentioned that before with LiDAR. Now, essentially, this is the concept of being able to work out where your rover is on a surface, which is quite important. If we don't know where we are, chances are we can't do everything that we've set out to do. So what I've got here on the left-hand side is what's known as an event camera. Now, these are quite nifty cameras where rather than recording the entire image, it's only looking for changes in pixel values. And so what that means is that even in really low light, such as here, where I've turned the lights off and you can't see the infrared image, you're still able to pick up where things are in the scene. Now, when I was talking before about the heavy shadowing that can occur on the moon, something like this would probably aid you quite significantly in being able to work out and track features. You've also got this idea of visual odometry, and they do this quite a bit on the Mars rovers, where you have really nice, well-lit scenes, and that's where you take multiple images as you're moving around somewhere. And what you do is you look for features between those images and you track them. So for example, as I believe this was Opportunity traversing along, it's tracked these features and it knows how far apart it's taken these images, right? So if it knows how far apart it's taken these images, it can work out how fast these pixel values are changing, and in turn work out how fast it's going and how far it's gone over periods of time. And they reckon that this reduced the localization error of that rover quite substantially, where in areas where there was high slip, so the wheels would just sort of spin and you couldn't pick it up with wheel encoders because they're just spinning, you're not sure if they're actually moving or not. This visual odometry was able to reduce that error quite substantially, below about 5%, which was amazing. So in addition to this, we can also do a couple of things that we do in traditional sort of satellite engineering. Satellites and rovers aren't all that different. They're both out there in space, and they both got to know where they are. And so one of the ways you can do that is, you know that a rover is sitting on the surface of a planet, right? And so if you can work out what part of the planet it's on by what is immediately, above it, you can then get a pretty good idea for where your rover is, and in particular, where your rover's pointing. So if you put what's known as a star tracker, so what this does is it takes a picture of the sky, there's a number of stars there, and it uses a database of where these celestial objects are to basically work out an angle to where you're pointing. It's essentially another camera, you just stick it on top, and this is able to give you a pretty good idea of a compass reckoning, so where you're pointing on a planet's surface in particular. The other thing you can do is, rather than have a star tracker, look for the biggest star in the sky, which in most cases is the sun. So this is a sunrise on Mars, and this is a pretty interesting and nifty technique that NASA came up with. And you've got this rover with these fantastic cameras on it, so you don't need a sun sensor. All you need to do is rotate your head around until you can see the sun. And we know with pretty good accuracy where things are in the sky, and so we can work the vectors back there to give a pretty good idea of where our rover's pointing. The other thing we can do is we can actually take a photo of our rover. So if we've got another spacecraft sitting up above, we can take photos of the surface and with pretty good accuracy know where our rover is. So this is actually Curiosity sitting on the surface of Mars. Now, if we know where our spacecraft is in our orbit, we know where it's pointing towards the Earth, we can then, again, do the inverse transform and get a pretty good vector, an idea of where our little rover is relative to that orbiter. I now want to take a bit of a step back, and I want to go back to the planoptic function. So this is sort of, we've moved out of what we've already done for spacecraft, and I want to look a little bit past that into some of the things that we could do to make spacecraft work a bit better and sense more things. And so you might remember that we were restricted by the aperture for a regular camera. And so what if we were to increase the number of apertures? Well, this brings into case the light field. Now, Don Dancero, who I work under, was very gracious enough to allow me to give this presentation in his stead. He thought I would do a good enough job. And so we're going to see how we go with this. Basically, a light field camera is one which has multiple apertures. And rather than just having a singular aperture pose, we have multiple. So here we have an XY array of cameras. We then are able to have two sort of axes, an additional sort of area of the planoptic function that we can work in. And so what we have is all these cameras and all these apertures imaging the same scene. So we end up with small little images next to one another that we can stitch and work out where they came from. Now, what's really special about this is in being able to work out where the light has come from, we can do some pretty nifty things where we can just select what light we want to take for our image. And so this has some pretty interesting results where we have already taken the image, it's already fixed in time. But if we select what light we use to compose that image, we can actually change the view of the camera. And most interestingly, we can change the camera after the image has been taken. So essentially completely reconfigure it in terms of focal length and depth. And so you might be wondering, this seems pretty weird. What are you talking about? Well, this is what it looks like. So this is from one of Don's papers. You can see here the little lorikeet, and this is taken out of the ACFR window. This is taken in a single snapshot in time. The camera itself is not moving. What we're doing here is we're selecting the light rays that make up this image. And the net result of that is we can slightly change the perspective. So things where, you know, this window could be obscured from one view, we can actually shift that perspective slightly and be able to see more of that window there, which is a pretty nifty and interesting technique, if you ask me. The other thing we can do is we can actually select what depth we look at. So this is basically volumetric depth of focus. And so this is a sort of showing off what it is, where we're selecting different widths or volumes of the scene to actually keep in focus, which is pretty interesting. Now, you might be wondering, what's this got to do with space engineering? Well, this is pretty cool in that we can only send one camera up, but reconfigure it after the fact to be any sort of camera we want within reason. And that's pretty powerful, right? The other thing we can do is we can actually sense depth. So knowing where the light has come from, knowing the angles it's entered the aperture at, and the pose with which that aperture was set to, we can actually work out basically how far away that light came from. So you can see here, this is quite a difficult scene. Some jacaranda flowers. We can actually work out the depth in inverse meters where these things were, which is pretty nifty. So if we were to throw this on a rover, that's very powerful. A camera that we can completely reconfigure after we've taken the images, and also depth, which is what we need to perceive it. It's also very computationally efficient. So everything is basically linear algebra. And this probably doesn't mean very much to you, but basically computers are very good at linear algebra. If we have an FPGA sitting on a rover, it can just do these matrix multiplications over and over again and crunch the numbers essentially, which is sort of begs the question, why haven't we put it on a rover sooner? But again, active area of research, and our sort of research group is looking at using these sorts of things in robotics. The other thing I want to sort of touch on here is this concept of synthetic aperture photography. So this is kind of a subset of light fields. And this, you can have a look at this online. It comes from Microsoft Research. Basically, we have a number of cameras set in an array, and we can stitch all these images together. The net result of that is we can actually see through things in front of us, which is really, really weird. Now, in robotics, there's a thing called active vision, which is where we want to track something. It might be a waypoint, it might be something in the scene. And occasionally, if something comes in front of us, well, that could cause problems with how we're navigating around. And so essentially, what we could do using this synthetic aperture photography technique is see through those occlusions, solid objects immediately in front of us. And you can see here this volumetric focusing idea, where this focus plane is going through depths in the scene. And as you can see, each of these individual pictures can't necessarily see this guy behind it, but combining them all together, we're able to effectively refocus only on that plane where that person's in focus, and take out of focus the things in front of him, which is quite, amazing, really, that we have the algorithms to do that. So This is all kind of algorithmically intensive, and it sort of, again, begs the question, is there a way to do it better? Can we make it a little less slow or a little less hard? You were thinking of neurorobotics, weren't you? Yeah, me too. Great minds think alike. So what is this concept of neurorobotics? And this is a really sort of old thing that is beginning to make a resurgence now. And it's essentially looking at giving robots a brain built directly into their hardware. And so essentially, we have these little electrical neurons that are not software defined, but hardware defined. We have sensor signals come in with some weights, and these can actually be sort of programmed by the robot by itself by experiencing new scenes. And the net result is we get some actuation out, whatever that may be. And this looks like the intro to artificial intelligence, right? And in a sense, it is. This is a hardware sort of brain cell that we can put on our robots. Now, what does this look like? Well, there was this guy in sort of the 1990s. He was on the Discovery Channel a lot, a guy called Mark Tilden. And essentially what he used to do was he was really into this concept of neurorobotics. So he designed all these robots to basically, they were made out of junk, discarded electronics, which is awesome. But he soldered on these sort of artificial neurons where things like touch sensors would come in as an input, and it would have some net output here. He used to make them on his kitchen table. I'm not sure where that's gone. My computer might be glitching out a bit. That's okay. But they were sort of weird, right? This one here was made out of Walkman. And what it's done is it sort of worked out itself that if it hits something, the neuron is going to fire and actuate and move it away, essentially. He's got another one where it'll seek out light. These are some really, really interesting robots. There are also other things that we can do where this sort of ties into the concept of biomimicry, where we look at concepts from nature to feed into robots to give us new sensing techniques. And so this here is something out of the University of Bristol called ShrewBot. And basically, it's got all these sensors on the front that are touch sensors, whiskers almost. And what it's doing here is it's actually building up a 3D representation of its environment solely based on the response of each of these whiskers. And it's able to build a map like that pretty well. This is actually very similar to what happens with shrews in real life, where basically they can't see because it's dark and they have all these whiskers on their nose and they're able to feel around for their prey in real time. So if we were to put these on space robots, who knows what we would get? This is still a very experimental field and there's lots of really awesome things here. And I encourage you to seek out some more examples of these because they are really just fascinating that we can take these concepts from nature and apply them to the real world. But yeah, neurorobotics, interesting space. So you might have noticed that I left out that lambda in the planoptic function a little bit. And so this comes to the part of the talk where I get to talk about some of the things I've been up to. So I have been working on 3D hyperspectral sensing for about the last almost 8 months, 9 months now. And I'm currently in the process of writing a paper with Adam Tarras. Some of you may know him from mechatronics. And essentially what we're looking at doing is using this idea that if we fuse spectral information of a scene, which gives us information about material and also the 3D shape of a scene, that we're able to reduce the amount of data that we've got quite significant. And so this could open up some brand new doors and frontiers where these hyperspectral sensors that produce a lot of data that's really, really big, make it a lot smaller and much more manageable. So this here gives you an idea of what sorts of things we're looking at. What I've got here is the visible wavelength spectrum of this 3D checkerboard I showed on the previous slide changing in colors. And these are the intensities of wavelengths that essentially we're stepping over. And you'll notice that this is mapped to a point cloud, so a 3D representation of the scene where we've got this color board We've got a background hanging behind us here. And essentially what we've done is align these two together. And we're able to basically generate a 3D scene, but under certain wavelength bands, which is a pretty niche sort of concept. So the way this works is every sort of incident spectrum of light bounces off an object in two ways, where we have a Lambertian reflectance, which is a diffuse reflectance. It'd sort of be like, I don't know if I can pull that in, this sort of back half of the mouse here where it's nice, smooth, a dark grey, and specularity, which is where these sort of white spots that direct reflections from light come from. And it's the multiplication of these two that we're able to pick up by a hyperspectral imager. These are also functions of the incident spectrum as well. And so this is sunlight, gives us a nice sort of flat spectrum, but you can have some spectrums which are not so nice. For example, the tubes that we've got in the lights here in the lecture theatre are likely to produce very sort of sharp spectrums. And so what this is, and it's kind of hard to get your head around at first, is this concept of a hyperspectral cube where you're taking an image, but it's 3D. So you have the X and Y as we've had before, but you then also have this spectral axis where we're looking at the intensity of wavelengths over the entire scene. So you can see the blue here is clustered in the blue spectrum. The grey, which is a sort of more dim white, as an example, has sort of a constant spectrum throughout, and the reds are quite clustered up towards the red end of the spectrum as well. These white bits of our dinosaur here, they're also pretty much constant throughout, and that tells us that we're getting nice hyperspectral data out of it. And so what is the use of this in space? Well, as I mentioned, this enables us to work out what materials are. And so robots are able to use this pretty effectively. And they've used this on rovers and space missions quite substantially for a while. They're able to work out what sorts of rocks and minerals are sitting around them. And they do this with some pretty high-powered spectrometers that are active, but you could also do a passive as well based off the reflected light. And so our sort of work is focusing on, well, what if we make this data slightly more manageable for these robots to be able to deal with? So the very last bit of the lecture, where to next? Well, there's lots of really exciting space missions coming up, and in particular rovers. This here is the Viper mission. It's going to the poles of the moon. This here is one of the upcoming JAXA missions that they've put out to tender, which is also going to the poles of the moon. And what they're looking for here is ice, frozen volatiles in the craters of the moon, where they basically want to work out, number one, if there's water there that we could use when humans go back to the moon, and number two, if it gives us any insight into the history of the moon as well. So the moon's a really active place as well. Obviously, Mars is quite interesting. It's a pretty good Earth analog, and understanding its previous life could give us insight into Earth's future life. So this here is the Rosalind Franklin ExoMars rover, which is essentially going to go to the moon after Perseverance in a few years' time. And you'll notice this has solar panels, so chances are it's probably not going to be there as long as Perseverance or Curiosity. And I believe this is the one that they've set to collect samples of Perseverance and return those back to Earth, which is quite exciting. Some news in the last couple of days is Ingenuity, the little helicopter sitting under Perseverance, has swung down from inside the rover body. He's actually put his other two legs down, but I couldn't find an image of that in time. And he's actually going to be flying in the next couple of days, which is quite exciting. So do stay out for that. Lots of exciting stuff happening in space. Basically, having the ability to sense up there, sense effectively, and work out what's going on in your surroundings is, immensely important. But it also helps us to do science, which is one of the main things. It's one of the main reasons why we do stuff out in space. If we understand more about our universe, we can most likely understand more about ourselves as well. And so that's pretty much it from me. thank you very much for sticking around. More than happy to take questions. Hopefully you've enjoyed. Hopefully you've got a bit of an insight into some of the things we do in robotic imaging. And yeah, all the best. Enjoy your afternoon. Thank you. There is some people in the lecture theatre here with me, which was quite nice to not be able to lecture only to a screen. So yeah, any questions? Yes, Steve has a question.
Where do you see the advances in space robotic imaging specifically going for the next like 5, 10, 20 years? Like, where do you think the most fruitful, interesting, like, steps forward are going to be?
Yeah. Okay, so just to repeat that question, so, I think Steve was unmuted for that, which was good. Look, it's hard to say. There's a lot of things that we're doing here on Earth currently that are really cutting edge, but we're doing them in labs, and we've sort of got to actually transition them out of labs and be able to put them on autonomous systems that can operate for extended periods of time. And so that, I think, is quite a great challenge. In addition to that, dealing with some of the environments I sort of mentioned before, there are things that we just don't have here on Earth that, unless we've already been there and we've worked out what works and what doesn't, it's kind of hard to say whether whatever we've designed is actually going to work. So that those ideas for burst imaging, might work, they might not. We just don't know as of yet. We don't have the moon here on Earth. We certainly don't have the Mars here on Earth. And let's hope we don't have Venus here on Earth, because that would probably not be very good for any of us. But yeah, I'm pretty sure that I think is going to be one of the main struggles, taking whatever our cutting edge we have currently in robotics and being able to apply it in a way that is reliable and able to deal with these unknowns.